Hi everyone, welcome to the channel. This is Ankit and I'm a senior software engineer at Google. Today we are going to cover a classic system design problem, that is designing a news feed for a popular social media website like Twitter or Instagram. While you can find many resources around this topic, I found that they often lack the detail and the structure needed for a real world interview. So today we are going to approach this problem as we would do in a real interview. And as we go, I'll share tips, tricks and frameworks for not only understanding the solution but also to effectively communicate the solution to an interviewer. So let's get started. Hi everyone, welcome to the channel. This is Ankit. So the first and most important step in any system design interview is to work with the interviewer to outline the scope and requirements of the problem and ask any clarifying questions as part of this process. Example, in this case, we could ask what type of content the news feed supports. Is it text only, or images and videos are also part? And is the feed chronologically sorted, or do we surface content based on some heuristics or some user preferences, etc. On a basic level, as part of this video, I would like to cover these requirements. So I'll start by the functional requirements. The first one being user should be able to make posts containing text. So this is the absolute core of a news feed, that is being able to create content. And for our initial design, we'll keep it simple and assume a post is just a piece of text. In real world scenario, we would also consider images and videos, but starting with text helps us focus on the core mechanics first, and this is our primary write operation. Next up, so we want to user should be able to see a personalized news feed. So this is the read side of our system, and it is the most critical part. When a user logs in, they need to see a unique feed content. For the scope of this video today, personalize means showing the content from all the users they follow in reverse chronological order, and this is the main feature we are designing for. Up next are the non-functional requirements. So these non-functional requirements are the qualities of the system and are just as important because they define how well our system needs to perform. These are the constraints that will heavily influence our design choices, and while we write down, it's important to prioritize the requirements which are unique to our system and what makes our system specifically challenging. So one of the most important qualities of a newsfeed system is that it should have low latency for fetching the newsfeed. We need the user's feed to load quickly, and we should aim for a sub-second latency of around let's say less than 500 milliseconds. This is a reasonable goal and a metric, and this ensures that including the network delay and loading the content, users would be able to see their content within a couple of seconds. One important requirement of our system is that our system should be reliable, and user shouldn't miss any post from any of their followers. So users shouldn't miss any post from any of their followees. And this is an important guarantee that our system should make. One other thing that a system should do is that it should surface fresh content every time user refreshes the home page or scrolls up. So a system should surface fresh content every time the user refreshes home page. This is a subtle and very important point. Every time a user refreshes their homepage or scrolls back to the top, they should see the very latest and fresh content that they haven't seen. This means that our system can't just be static, it needs to be dynamic enough to show the new posts as they come in. Also, our system should be scalable to the growing number of users and posts. As more users join our platform, and as more posts are created, our performance should not degrade. And there you have it. This is our complete blueprint. With these requirements clearly defined, we now have a solid foundation to start our design. Hi everyone, welcome to the channel. This is Ankit. Alright, we have defined what our system needs to do. Now let's think about how a client, like a mobile app or a web browser, is going to talk to our backend. This is where we define the APIs. APIs are the contract between the client and the server, so they are a crucial first step. Let's start with the write API first, that is one that handles a user creating the post. So we'll be using RESTful semantics for defining the APIs. For creating a new post, we will use a post request, and with our endpoint being v1 posts. So we are notice we are using a plural post. This is a standard RESTful convention that makes our APIs more intuitive and scalable, and it suggests that we are interacting with the collection of all posts in our system. Now, what does this API need to receive from the client? Definitely it needs the post content. So post content could be sent in the request body in a JSON object. So it will have the content and any other important fields. And the information about the user who is posting this content can be sent in the request headers as part of some authentication tokens to ensure that user actually has the permissions to make a post on behalf of this user, and user ID of the ID of the user can be derived from this authentication token. And so what this API would return is it can return a post ID of the newly created post, which is unique, would be unique in our system. So that's our write API. Now let's define the most important API of our system, that is the read API for fetching a user's newsfeed. Fetching the news. So for fetching the data, we'll use a get request, and the endpoint will be v1, let's say me feed. We are using me as a shortcut to represent the currently logged in user, and this is a common practice. Now here's a crucial point. Users newsfeed can be massive, that is potentially infinite. We can't send all of it in a single request. This is where we need to use pagination. So we'll use two parameters in our API to handle this. The first one is the page size, and second one being the cursor. So page size tells how many posts do we want to return in a single page. For example, 20 posts. And the second parameter is also very important, and it tells it is the unique identifier from the last post a user saw, like its ID or a timestamp. So this tells our system exactly where to start fetching the next page of results. This is more reliable than using an offset because it prevents users from missing new posts that might have been added to the top of their feed while they were scrolling. So this is how we fetch a user's personalized news feed, and efficiently and reliably. So the response from this API would be could be a JSON object containing a list of posts, post 1, so it will have the ID, title, content, user, author, timestamp, profile pic of the user who posted, etc. So yeah, this will be a list of posts. By defining the APIs, now we have a clear contract to build our backend services.
Hi everyone, welcome to the channel. This is Ankit.
Alright, we have outlined the APIs, but a design is meaningless without understanding the scale we are building it for. This is where we get into metrics and estimates. This part of the interview is where you can really impress by demonstrating your thought process and understanding of what drives the design. The goal here isn't to get the numbers exactly right. It's to show you can make reasonable assumptions, perform some quick calculations, and use those numbers to inform your architectural decisions. So let's take a look at our traffic estimate and numbers. Assuming that we have around 100 million daily active users on our platform, and on an average each user refreshes their feed 10 times a day. With this, we get a total read requests of which is 100 million into 10, which is 1 billion read requests per day. So to get the throughput or the request per second, we'll divide the these requests by the number of seconds, which is, and which is 1 billion divided by so this is 10 raised to power 4, which is 10k requests per second. So this would be the average number, and traffic isn't always evenly distributed. A common rule of thumb is that a peak traffic can be 2 to 3 times the average. So let's say our peak QPS would roughly be around 3 times the average, which is 30k requests per second. So this is the read QPS or QPS for the newsfeed. Now let's also take a look at the write QPS. So assuming read is to write ratio of 100:1, and this would be a fair assumption for a newsfeed application like Twitter, where most of the users are consuming the content. And with this, our QPS of write QPS would be 330k divided by 100, which is 300 requests per second. And this is a much smaller number. So these numbers immediately tell us something important. We need a system that is highly optimized for reads. The newsfeed API would be one of our biggest bottlenecks, and we need to design our system to handle very high QPS with low latency. Next up, let's see our storage estimates. So we need to store the data for all the posts in our system. Let's assume that average post size is 1 KB. This accounts for text, content, metadata, any image, URL, etc. So we have around 1 billion read requests per day, and with a 100:1 QPS ratio, we would have 10 million posts per day. And so with this, we have a daily storage requirements of would be 10 million into 1 KB, which is around 100 GB per day. And over 5 years, we would roughly need 100 billion per day into 100 GB per day into 365 days per year into 5, and this roughly comes out to be 200 TB of storage for posts. And this one is per day. So we are talking about a massive amount of data and a significant number of requests. The 200 TB of post data tells us that we need a highly scalable and distributed storage solution. Walking through these numbers not only gives us a clearer picture of the scale, but also justifies a design choices later on, and it's a foundational step that sets up the rest of the design. With these numbers in mind, we are ready to move on to the high level architecture.
Hi everyone, welcome to the channel. This is Ankit.
Now let's start with the high level design. The goal here is to satisfy our core functional requirements, and we're going to use a microservices approach which breaks down our system into smaller, more manageable pieces, each with a specific job. So I'll start with the client on the leftmost side. And the client will be our mobile app or browser. The first thing is that the request from the client would hit an API gateway. Think of API gateway as the main entry point to our system. It's a single central point that handles all incoming traffic and handles things like authentication, rate limiting, and routes requests to the correct services. Now let's trace what happens when a user posts something. The API gateway routes that request with the content to a dedicated service, and I'm going to introduce PostGrid service for this. So CRUD stands for create, read, update and delete. The service's job is simple, that is, it handles all the create, read, update and delete actions for a post. Upon receiving the post request, the service would receive the request and write it to a database, which is the post DB. Upon writing the information, the post DB will include the following attributes: post ID. So this would be the primary key, which will be generated by the database itself, and it will have the content, user ID, ID of the user who posted the content, metadata, timestamp, etc. A smart choice for a post DB would be a NoSQL database like Cassandra or DynamoDB, so that it is easily scalable to the data volume. So this is our write path. Now let's take a look at the read path, which is fetching the news feed. So when a user opens their app, the API gateway routes this request to another service, and let's call it newsfeed service. So we made this a separate service because the logic for building a timeline is complex and resource intensive, and by having a dedicated service we can scale it independently to meet the high demand of read requests without affecting the other parts of the system. And to build the feed, the newsfeed service needs to know who the user, who all users the current user follows. So it first talks to another service, let's say a relation service. So relation service manages all the follower and followee relationships in our system, and the data is stored in a relations DB. So once the newsfeed service has the list of follower IDs from the relations service, it then goes to the post cred service to get the latest posts for each of those users. This process of retrieving posts for each user is called fan out, and since it happens when we read the post, we call this fan out on read. Additionally, the response should also contain the information about the user who posted, that is their name, profile pic, etc. So the newsfeed service would use the user ID in the post to fetch the information about user's name, their profile pic, and return the response in a single object to the client. So this is a very basic high level way to generate the feed, and this is our initial high level design. It satisfies our core functional requirements, but as you might guess, this isn't going to scale. Getting posts from hundreds of different of users for every single feed request is a massive performance bottleneck, and this brings us to a deep dive where we'll explore how to make this system much more scalable.
Hi everyone, welcome to the channel. This is Ankit.
This is where we move on to the deep dives and we take our high level design and evolve it into a robust and production ready system by addressing our non-functional requirements. Our biggest concern is making sure the newsfeed loads as quickly as possible. As we identified in our metrics, the read path is our most frequent and critical operation. So our design must be highly optimized for reads to achieve the sub-second latency. And we have identified a major bottleneck, that is fetching the feed on the fly when newsfeed service receives the request for each user. Hitting the post DB repeatedly for every user's feed is going to be incredibly slow, and we won't meet our latency goal. To dramatically speed up the read path, our core solution is to pre-compute the newsfeed for each user, and we'll store these pre-computed newsfeed in a fast in-memory cache, which we'll call our newsfeed cache. So this will be a newsfeed cache, and for each user ID we'll have a list of post IDs to be shown in the newsfeed of that user, and the newsfeed service will query this cache and return the results to the client. So how it will exactly work is, when a user creates a post, our postcred service now does two things. It writes to the post DB, and it also sends a request to our fanout service to update the newsfeed cache, and it will do so by posting the post ID to a queue. Let's call it post queue. So this queue is a decoupling point. It means that postcred service can finish its job and return the response to the client or user, satisfying a low latency requirement for the post, and a dedicated fan out service dedicated fan out service listens to this queue. Its only job is to fan out that post to the relevant users. So what it does is it would get the list of followers for the user who created the post from the relation service, and then it would for each of those followers it would write the new post ID into the into the list of their pre-computed news feeds. And this process is called fan out on write because the post is queried for all the users in advance. And this newsfeed cache is a secret to low latency reads. The newsfeed service now simply fetches a user's pre-computed feed directly from this cache, which is incredibly fast. Now, how big does this cache actually need to be? We can figure this out by a quick calculation. Let's recall our assumptions from our metrics and estimate section. We have 100 million daily active users, and for each user, let's say we cache the 500 post IDs per user, and let's say for each post ID will take around 16 bytes per post ID. So this is including the post timestamp, the unique ID, and so for 500 posts we'll have around 16 by 500 to 16 bytes, which is around 8,000 bytes per user, which is roughly around 8 KB of data per user. So each user's newsfeed cache takes around 8 KB. For 100 million users, our new total storage would be around this is around 800 GB. So our entire newsfeed cache for 100 million users only needs about 800 GB of data. This is a fantastic number, and it tells us that we can comfortably fit all our newsfeed data into a relatively smaller cluster of Redis instances. Now, how many Redis instances would we need for this? Let's assume that a single high-end Redis instance can handle about 100 GB of data. We'll need around, which is 8 instances. So we need around 8 primary Redis instances to hold our data, and of course for high availability and fault tolerance we'll have a replica for each primary. So we'll likely start with 8 instances in total, and this is very scalable and manageable solution. So this calculation proves that our idea of a newsfeed cache is not only a good design pattern, but it is also feasible and a cost-effective solution at scale. So we have built a really great system. An issue with this approach is that, let's say there is a celebrity on our platform with millions of followers. A single post from them could overwhelm our fan out service. It would have to write that post ID to the newsfeed cache of millions of users all at once. So this is a classic thundering herd problem that can cause major performance issues. To solve this, we use a hybrid fan out strategy. So for a vast majority of users who have a normal number of followers, our fan out on write system works perfectly, but for celebrities with a high fan out of users, we'll switch things up. And here's how it will work. For a user with millions of followers, our fan out service will not fan out the post to all of their followers. Instead, it does the following. So for one of these followers requests their newsfeed, the newsfeed service does two things. The newsfeed service, it checks the newsfeed cache to get the pre-computed posts from the users they follow. It also checks with the relation service to see if the user follows any high fan out accounts. If it does, it directly queries the it directly queries the postcard service for to get the latest posts from those accounts, and it then merges the two set of posts, the one from the cache and the one from the database, and displays them to the user. So this approach gives us the best of both worlds: low latency for the vast majority of users and a scalable solution for our high-end, high traffic celebrity accounts. Now, now let's say when the newsfeed service, it would get the list of post IDs. It's just a bunch of numbers. It still needs to fetch the actual post content from the post DB, that is the text content, user's name, and so on. If we hit our post database for every single one of these posts, will create a bottleneck. So to handle this, we can introduce a cache in between post DB. And here is how it will work. When the newsfeed service gets a list of post IDs, it doesn't go straight to the database. Instead, it would first check with the cache via our postcard service for the full post objects. Since most of the posts people see are recent, the chances are very high that the content is available in this cache. This means we get a very high cache hit rate. This two-tiered caching strategy system ensures that everything that a user sees, from the list of posts to the actual content, is served from high speed in memory cache, and and with this we completely minimize slow database lookups, and as a result our newsfeed loads incredibly fast. Now let's move on to our second non-functional requirement, which is reliable delivery of messages. So far we have focused on speed and latency. Users also need to trust that our system won't lose their posts or make them miss out on their friends or followees' content. This is a crucial and often overlooked part of designing a news feed. It's not just about the speed, it's also about accuracy and ensuring that users see everything they are supposed to. So there are two main areas to focus on. One is ensuring reliable delivery, and the other is handling real-time updates and pagination. So for the first part, that is ensuring that every single post gets delivered to every single follower's feed. So we are using a post queue, message queue, which has this content. It has the post ID and the user ID of the user ID who created the post. So now what happens if our fan out service fails, or the processing fails in between? So a message queue should ensure that every message that is sent is persisted in the queue, and if our fan out service goes down, the messages are safely stored. When the service comes back online, it can continue processing the backlog of posts exactly from where it left off. And fan out service wouldn't just read a message and move on. It would also acknowledge, and only when it acknowledges that a message is successfully processed after after the newsfeed cache is updated for all the relevant followers, uh, only then the message is removed from the queue. If the service crashes midway, then the unacknowledged message remains in the queue and will be reprocessed by another instance. This guarantees that no post is ever even silently dropped. Now let's say we have around a user has multiple followers, and fan out service has processed the post ID and updated the cache for some of the followers, and uh, let's say it crashes in let's say our cache update, our cache is not available. So uh, our fan out service can simply push these failed tasks, that is the follower ID and let's say in another queue, and can call it retry queue, and it will have this information, follower ID and post ID, and another worker for this queue would be let's say it's called retry worker, and this this worker will would then retry processing of this failed task after a certain delay and add it to our newsfeed cache. So this retrying can be done with an exponential backout strategy where the delay between retries increases with each failed attempt. This prevents the thundering herd of retries on a temporarily overloaded cache, and this ensures that our posts are reliably delivered and updated in a user's newsfeed cache. Now, even with a reliable fan out, users can miss a post if our pagination isn't handled correctly. A common mistake is using offset based pagination, that is, give me 20 posts starting from the like let's say 21st post. This is problematic because if new posts are added while a user is scrolling, the content shifts and they might accidentally skip some posts. So better approach is a cursor based pagination. Instead of an offset, we use a unique immutable reference point, a cursor, to mark the last item we have seen. So how it would work is, when a user first loads their feed, the newsfeed service will get the first 20 posts from the newsfeed cache and returns to the user. The cursor is the post ID or timestamp of the very last post in the list that is returned to the client. When the user scrolls and requests the next page, they send the cursor back to the newsfeed service, and then service fetches all the posts that are older than the cursor, ensuring that user gets the next sequential batch of content without skipping any new posts that might have appeared or when the newsfeed cache is updated. So this method guarantees that a consistent stream of content for the user, regardless of how many posts are being added, created or deleted from their timeline. Another user experience challenge is handling feed freshness. When a user pulls to refresh, they want to see new posts. But how does our system know what's new and what's already been seen? So we have designed the API with page size and cursor for infinite scrolling, but a pull to refresh is different. User isn't scrolling down, they are scrolling up to see what's been added since they last refreshed. A naive approach would be to return the same posts they saw if nothing new has been added in our cache. So the user experience would feel broken with this, and we definitely don't want to maintain a separate scenes post database on the server for every user, as that would be incredibly complex and resource intensive problem to manage at scale. So the solution to handle it would be on the client. That is, client would maintain a list of seen posts and let's say it has some list of post IDs which have already been seen. So this list would be updated on the client when the user is scrolling. Each time when a post is displayed in user's viewport, that this list that post ID would be added to this list. So client application will track all the the client application can track all the posts that have been displayed, and when a user pulls to refresh, that is client would make a newsfeed request without a cursor or a page size. It simply asks for the newest posts from the newsfeed service. So our newsfeed service sees this request and knows to return the absolute newest post available in our cache, and service doesn't care what the user has seen. It simply provides the latest content to the client. The client then receives this list of new posts, and if the client will now merge the new list with the posts already seen on the screen. So, and it will, for each post, it will check if it is present in this list, and if it is present, then client can intelligently choose to skip that post and instead check for the next post, and so on. So this is a much more scalable and efficient design. The server only has to worry about fetching the latest data, and client handles the presentation logic. So this intelligent or smart approach on the client can help improve the user experience by ensuring feed freshness and ensuring that users see the latest content which they haven't actually seen. So we have covered latency, reliability, and feed freshness, but none of it matters if our system can't handle a massive number of users and posts. So let's talk about our final and arguably the most important non-functional requirement, scalability. We are talking about a system that can grow from millions to billions of users without failing over. So based on our earlier estimates, we know that we are dealing with a massive amount of data of the order of around 200 terabytes, and this is a huge amount of traffic and tens of thousands of requests per second. The reality is that no single server, no matter how powerful, can handle this. So our solution would be horizontally scaling. Let's talk about our database. So if we put all our post data into a single post DB, it would become a bottleneck. Reads would be slow, writes would be slow, and would run out of storage space. So we need to split our data across multiple servers. So this is where we would introduce partitioning, database partitioning or sharding. And this is the process of splitting the data across multiple smaller databases. The key decision here is to choose the partitioning strategy. That is, how do we decide which data goes on to which server. For our newsfeed, the most logical and efficient partitioning strategy would be to shard our database by the user ID. So this will be a shard key. Because our most frequent and critical queries are tied to a specific user, that is retrieving a user's timeline or getting the post from a people a user follows, etc. And by sharding by the user ID, we can ensure that all of a single user's data resides on one server. So when a new post is created, PostGrid service will take the user ID and apply a hashing function to get the hash value, which will tell which specific database server to write the post to. And this design gives us a fantastic data locality. When the newsfeed service needs to fetch users post, it knows exactly which database to query, which turns this global query into a single localized query, and we can handle an almost limitless number of users by simply adding more shards as our user base grows. So this sharding strategy helps our databases to scale the storage. Additionally, we also mentioned that our services are stateless, that is both PostGrid service and newsfeed service, and this is absolutely critical for scalability. It means that our it means that we don't store any session data or user specific information on the server itself, and this allows us to scale horizontally with ease. We can simply add more instances of these services behind a load balancer, and any request can be handled by any of the available instances. And with that, we have covered the complete system design for a newsfeed, from our initial requirements to a scalable, low latency and a highly reliable architecture.
Hi everyone, welcome to the channel. This is Ankit, and with that we have covered the complete system design for a newsfeed, tackling it exactly as we would do in a real interview. So what are the key takeaways? If there is one thing that I would like you to remember, is that a great system design isn't about drawing a perfect diagram. It's about your thought process. It's how you take your simple design and justify the choices by data, and how you weigh in trade-offs. I hope this structured content would help you give a framework to ace your next system design interview. If you found the content helpful, please give it a thumbs up and subscribe for more in-depth information like this. And if there's any topic that you'd like me to cover in subsequent videos, please leave comments. Thank you for watching the video. Happy designing.